But it could be that the tests are not here, but we're left with Andrew, so we get tests. So,
Okay, it's all yours.
okay.
There's this one.
And there was a. When do you have your so you did from your computer?
Yeah.
Oh, okay. So I'll just use the this. Okay. So what I'm going to talk about is directly related to what Wayne just talked about. Some of it I'm gonna skip because it covered. But feel free to stop me if you want a wiki that stuff. So what I hope to provide you today is information about the beam attenuation, which is also called BC or the extinction coefficient. So all that is interrelated in the literature. So you see extinction coefficient, beam C or beam attenuation. We're talking about exactly the same. We talk about why we measure beam attenuation, how we measure beam attenuation, how does it vary in the ocean as function of space and as function of time, and also creative ways to use it to study ocean biology. And Wayne, you don't mind, while I'm talking to you, can you bring the board as well? So I need to recommend that. Thank you. Thank you very much. So within the context of the class, it's this Wednesdays, Thursdays scattering beam attenuation build up. Okay, so the reason we use beam attenuation primarily is because it relates to constellations of particular and it's the longest IOP for which we have commercial consumative. Since the 80s, commercial sensors have been built before Boston and before. So you can directly, now that's much shorter than the Sackies. Sackies goes back to the 80s, but the Sackies does not measure the full ocean, don't go like that. Even the first one were deployed in very deep depth, like 4,000, 6,000. The time period from 6,000 meters in the ocean was the first commercial scientists from a project called Hubble. Okay, so what do we measure? The principle is very simple, is we measure how much makes it to a detector. So we need a source, we need a detector, and it's, I light the light, and how much from me makes it to the detector that's right. And in order to make it to the detector, it shouldn't be absorbed along the way, and it shouldn't be scattered along. Okay? The beam is collimated. That means it does not spread as it goes out. Or minimally spread, because they won't spread, but minimally spread as it goes out. And the source can be a laser. The polarization of the source does not interfere with your ability to see the standard. So you have pulsar like in the list, which are laser source, and you have regular implant pulsars that have an LED. Both will give you, in principle, the same beam. And alignment is important. If your detector is moved to the side, you're not going to get the beam into it. So these instruments are really important to maintain alignment. And here I'm giving you an example of two of such sensors. These are both, they're called, you remember the name of these now? C-stars. C-stars. They're both C-stars, single wavelength. You find them at 532 nanometer for people with LiDAR, typically 660 nanometer. Any idea why 660 nanometer and why do we have variable? This is natural gravity. Exactly. That's avoiding, if you're interested in particles, and typically people using those are interested in work on standard mass or DOC, they don't want CDOM to affect the night. Because CDOM is exponentially decreasing, you get a measurement of mostly particles. That's a piece of that. Why different pattern? Pure water. Pure water absorption is the same flow. Well, what 10 centimeters was 25.
Well, is it the one on the red green line?
No, no, it's.
Oh, oh.
That's. Yes, so you adjust the pathing, just like you did yesterday in the lab. To the concentration of material you have, in order to two things. One is because we talked here about scattering. You don't want to have multiple scattering impacts. You don't want multiple scattering to bring stuff back, but in particular, you want the sensitivity. You want sufficient light. And I'll talk a little bit more about it in a second. Okay, so how does it work? We have a source. Typically, we have a window. You saw here, we need a window because you cannot do the electrons in the water as it is. So there's this window. And then there's another window. We have a sample in between. And then transmitted. We measure what's transmitted. And from yesterday, we know that this function is exponential. With now L here is not radians. I'm sorry, L is length, distance. And plug this up, and I'm going to use L for. So, and if we think about C as being concentration times material specific attenuation, then this tells us that what makes it to the detector varies exponentially with the amount of material I have. Function of concentration. Decreasing exponentially. That means that for every, for each time I double it, I'm going to certain proportion will go down as we go. Similarly with length, if I have a constant concentration, and this is length, it's going to go down exponentially. If I double the length, if I double the length, so if I double the length, this exponent is just twice as large. So I get the same proportional decrease in one versus in the other. The same proportion. Just like your bank account grows in proportion, this is the proportional law. If the first year, if you use 30% of the lights, from the first to the second, you're going to lose another 30%. Not linear, it's not going to lose the same amount in your first as you would in the second. And that's really important. You can approximate the linear only in the beginning, but very fast it's not linear. And again, beam attenuation is a sum of absorption and scattering. There are two things cause the extinction of light or the loss of light in the beam: absorption along the path, scattering out of the path. Is this clear? And the same is true. I mean, for the moment, I didn't talk about particles or dissolve, but that as you saw yesterday, we can use the transmissometer to measure dissolved substance. Okay, so this, we call this ratio the transmission. And sometimes you're seeing people doing the percent transmission. They take this, so the amount of light getting that we measure, divided by the amount of light we're putting in, and multiply by 100, that's our percent transmission. Additive with both concentration and substances. So I can add all my, and this is one of the beauty, because that is, so once I do, I think I said that this transmission is equal to e to the minus CL. Now, if I do the log of both sides, I'm going to get minus C times L equal the log of phi t equal to 0. And finally, my attenuation equal minus 1 over the path length log of phi t over phi c. So path length is important. This is back exactly the same error you saw yesterday in the talk, exactly the same. Didn't invent anything new, except that now it's on its own trace. And it's the log, it's proportional to the log of the transition. And this is linear. This I can add. I have two materials that I'm putting in the water. One is C1, one is C2. The combined attenuation is going to be C1 plus C. Very useful. If I double it, and I just did it yesterday in the lab with the dye, you add another, then I'm getting to C. My exponential is going to be this twice. Okay. There's several assumptions when we do the measurement, is that there's no interaction between the components. They don't interact between them. I can assume that they're independent. They don't. One doesn't cause the other to behave differently. And that's important because in a slab, if I look at light going through a slab, everything is attached. There's coherent scattering between the elements. Right, so it's going to behave differently than if it's just a bunch of randomly distributed polygons, which are not interacting. So here we're talking about non-interactive material. We also we like to be in the single scattering regime. So on average, if it scatters, it has one. The scattering that we care about is one, and the other is monochromatic. We want to have a minimum range of light because different wavelengths are going to act differently, and you're not getting necessarily the average of the lines behavior. It's going to be some nonlinear averaging. Okay, so now in reality, a sensor rarely measures the average. Some instruments do monitor changes in light intensity, but they don't measure it coming into my sample, but we do measure what comes out. So often what we do is we do it relative to a reference material, just like we did yesterday. Let's assume I do a measurement with water, and then I do a measurement with my sample. This is exactly, and then one minus the other will be my sample relative to the reference. Okay, so if I zero it on, if this is my water, then I can simply do simple algebra with IOP. Now, how do I come to this? This is simply, remember, log A minus log B. I do this term minus this one equals log A divided by B. Okay, simple logarithmic rule. So this is algebra. And it's important here that we have a stable source, stable enough that it's going to be assumed the same when I do the reference measurement as when I do my sample. And this is basically what we did yesterday with dissolved liquid. Exactly. Measure the reference, which is water, measure the sample, and the difference between them is going to be the way here. Is that what comes in? It's the light coming into your sample. Yeah. But you can see that here, it's not anymore. It's not anymore. It doesn't appear anymore. As long as this is stable, it's the same. I don't need to know that. Which is powerful. But then I don't need to monitor my source. For its exact output. I can monitor it's not changing, but I don't need to know exactly its output. Is this clear? Questions? So these are the fundamental of, okay, awesome. Somebody did a thumb up. But then I forgot to tell you something. Of course, we forget all the time to tell you something. What is it? Is that, there's two windows. I have a window here and a window here. And my light goes through windows. And the way a window, light goes through a window doesn't depend just on the properties of the window, but also on the property of the material you're going into. If you're going from a quartz window into water, you're gonna get much more light into your sample than if you're going from quartz to air. There is a reflection back into your sensor by the interface. Because water and glass are closer in units of refraction than glass and air. Or if I'm doing this measurement with dead seawater, which we need, more light is gonna make it in than if I do it in dry water in my lab. And we filtered dead sea waters and we got negative attenuation in the beginning of our life. Well, because the Dead Sea is 200 meters below sea level, 400 meters. No, it's simply an issue of transmission. So you have to remember that it's in your measurement, there are also these surfaces, and you can take them into account. It has to do with this transmission and this transmission. I have it on the slide. Let's see. Maybe I don't see it here. It should be. It's the next one. Here it is. This transmission is only a function of the index of refraction of glass and water or glass and air if you're doing it in air. So if you wanted to calibrate in air, do an air calibration, which people used to do, then you need to adjust for the fact that your transmission between the window and the sample is different if you use air and water. And if a person here would like a project, is looking for a project for this class, I suggest, how about checking whether we can use air calibrating this? How well does it work? If you do adjust for the glass, can you use air as a calibrator? I was told when I started you should never do that, but I've never checked it. So if somebody's looking for a project, it's not a hard project to do. Do measurements with air, do measurements with water, and see if the difference between them can be explained simply by the differences in temperature or not. And how they like that. So we talked about aerosols and we talked, yeah. So then again, when I do my sample, if this is not changing between my sample and my reference, by doing a ratio, I can get the transmission, the information I want, the beam attenuation of the sample. But that assumes that I have the same transmission properties between my sample and my reference. So how do we choose pathway? We want to minimize signal to noise. So there is a whole calculus of how you do uncertainties. And you don't have to get in straight details to it, but we want to minimize multiple scattering. The uncertainty is if C, beam attenuation, is the log of transmission divided by L, and there should be a minus sign, then delta C can be expanded in a Taylor series of units. It's delta of log TR divided by actually it should be delta L, sorry. So there's two things, delta L divided by L squared, is delta transmission divided by transmission, because it's log times L, and then delta C over C is delta L over L. That's your first, how well you know the path length is a source of area relation. And the second has to be with delta transmission over transmission divided by log transmission. So it has the largest relative error in the true extreme when the transmission is 1, when all the light makes it to the receiver, and when no light makes it to the receiver. That's when we have the largest uncertainty to the receiver. And somewhat in the middle, we have a minimal relative uncertainty. It turns out it's when transmission is 1 over E, or when C equals 1 over L. That's your sweet spot where you get the least amount of uncertainty, relative uncertainty in the beam attenuation. So with a 0.25 sensor, that would be at about a C of 4. With a 10 centimeter sensor, that would be about a C of 10. So you can kind of, depending on the environment, you can tailor, this is how you tailor your sensor to your environment. Questions about the previous thing? Okay. The next one has to do with something else with the measurement reality, and you heard some about it. It has to do with the amount that you're detecting. In order to get a measurement, I need to have a detector that detects light. But if I detect light, some scattering, forward scattering, can make it into my detector. So there's this, how would I say, there's this tension between, I want a lot of light so I get a good measurement, but I don't want to collect forward scattering. So there is this detector and there's an acceptance angle to go with it. And your measurement is going to be balanced. Because as you saw in Wayne's VSF or forward peak, every time you open it more, much more light streams in, because most of the light is scattered forward. But that's scattered light. Well, scattered light is now I'm calling transmitted. But I cannot close it to zero because then no light comes in. And it turns out every transmissometer on the market has a different acceptance angle. This one is 1.3 degrees. The ACX is 0.9 degrees. Which one would give you a higher rate of transmission in the water in front of you? This one? This collects light, so this will be smaller, this will be higher, more it gets more. And if this is higher, speed is going to be lower. Because more makes it in. So there's less attenuation by the way. So this, you're right, this will measure more at the detectors, but that means that less attenuated by the water. And I have an example here of several of such sensors that we deployed in Martha's Vineyard. We had an AC9 with a fast centimeter by 0.93. We had the least B and the least flock. And the differences between them were really large. Turns out, even from petrol, that up to 30% of light is scattered in the university. It's huge amount of light that you're losing. And indeed, so we have the least B here, and look how much different, much less light makes it into the detector of the least. And if you do ratios between the beam attenuation, so here is their values, and we can see the flock is the highest beam attenuation, second highest is the least B, third highest is the AC9. And in some cases, these are the ratios. So these are the ratio of least B to least flock. It's about 80%, between 80 and 90% of that. Then I have the ratios of the AC meter to the least B, that's the blue here, and then to the least flock. And you can see 40% attenuation. And these are the histogram of these guys. This is a time series at about 12 meters of water, a meter above the bottom. And so you can see that, wow, I'm just changing. I want to tell people what the beam attenuation is in the water, but I can't, because it means something going to be a different value. So that it means that your acceptance angle is part of the description of the beam attenuation. Beam attenuation is a function of acceptance angle. So if you're interested in knowing what you're likely to measure in water, make sure that if you read a paper on this water, they tell you something about what instrument they use, because it's instruments are going to give you the attenuation. Now, there's another reason why you don't want to have a very restricted sensor in the rear forward, and that's the blobs of water of slightly different temperature and salinity scatter light. And so that's going to be what's called scattering by turbulence. There's a nice paper by Gursky, there's a whole other paper. And so if the smaller you make it, suddenly turbulence is starting to affect your measurement. And as much as you like turbulence, it's hard to imagine it as an IoT. I mean, it does affect the transmission, but it's a problem that's going to change with the dynamics. So we don't want to account for that if we can avoid it. It's not a problem. It's not about your chemical property of the water, physical property of it. So by having a wider acceptance angle, we're less affected by the. And yes. What about holding instruments and being there? Into what was given, does it matter on the transmitted? What's important is that the beam be collimated and bigger than the hole. It has to be the beam, the hole needs to be within that beam. But not you, I think, I don't know that it matters that much.
You don't ultimately lose by the optics, the side of the. You have a bigger beam, but it's harder to walk in.
Yeah. So you have a beam and you have a hole to weaken the other. But then the bigger that beam is, the more light you're not using. So you want that, yes, you want to. Another thing that I just thought about, if you use the list and you deploy the list like the one we have, and you deploy it in the river where there's strong changes in its refraction, you solve the temperature, like you have in that level, you'll find that as you get to the vertical clearing, as you get into the transition between fresh and salty water, the beam is going to start wandering about you, and you'll be seeing extremely unstable and also very high. If you pass it through a hole or through a transducer, then you have no issue with it. You have no need necessarily being transition. So some of these stability max may be due to the technology developed that was deployed. It was sold to be max because it got an attenuation max, it will not be max. There are to be max, I'm saying not. When you use an instrument like this, particularly when you pump through it, it mixes the water and you don't get as much effect of turbulence. That's not the point. Yeah, it depends if you want it or not, that's up to you. It also, this also will break the particle in the past. Some of the larger are negative. So you are affecting what you're measuring. That's the, it's like in physics, the Schrodinger, it's not, is it Schrodinger? No, it's the principle. Heisenberg, yeah, it's the fact that every time you make a measurement, you're affecting the environment that you're working. And we're affected. Put an instrument on, we're affected. We always think about how we affect. Okay, so when you do measurements, as we talked yesterday, sometimes it could be that your reference material is a deep water mass, because you cannot make clean enough water stably on the vessel that works well for your instrument. And there's another wrinkle we have not talked about, but we talked about when you use these instruments, is that your measurements, your detector gets a signal even when there's no sample of the water. Even when no light is it, there's what's called the dark. And you have to correct for that. And when you work with these sensors, you have to account for the fact that there's a dark signal when you're not measuring. So the equation becomes something like this. Your sample minus dark divided by your reference to get your true gravity of the water. And that's important. Why am I emphasizing to you guys? Because you're going to go on oceanographic cruises, and on every American boat, and I suspect it's also in Europe, something like this is both inline and on the riversides. And very often, the people that deal with it don't understand these measurements, don't know you need to do a dollar. So they don't do dollars, so use the dark of the factory. The measurement can be significantly different than the dark of the factory, and that will be important in very clear water. It's not, this is a small value that's not that important in coastal environment, but in clear ocean water where you want the data, knowing that dark is really important. And that dark you get by very, very simple measure. You're putting something on the detector so no light goes in, and you're measuring what the hole is. It's not a hard measurement that people don't do because they don't know what to do. Now that you're part of our community, we want you guys to be good ambassadors and teach people about it. Another thing, how many of you heard about the diffuse attenuation? The diffuse attenuation coefficient is something that's measured often. It's measured by having a radiometer go up and down in the water and measuring how light changes. That's the diffusion. You have the light, the sun is the source, the sun is your source, and you're measuring light, and you do exactly the same idea. You have light as functional. You're measuring light as functional. These things. So let's say it's E. We're gonna get to next week. So it's gonna be E0, e to the minus kd, and now it's that. Very similar equation. Equation is the same, exponential decay. We measure the wavelength and we get a kd. But the source is the sun and the sky over the whole ocean, getting into my sensor from all directions. I'm collecting it with a collector. It doesn't look just up; it looks everywhere. Okay, that's the diffuse attenuation that we're measuring here. This is the beam attenuation. I have a source that's very much constrained, and I have a sensor that only looks up here. It doesn't look everywhere; it just looks into towards the source. So which one do you think is going to be higher? Which one is going to give me a higher attenuation? The beam attenuation or the diffuse attenuation? Beam is always higher. It turns out that the diffuse is mostly affected, and we'll talk about next week, by absorption. While this one is mostly affected by scattering. Scattering tends to be higher than the. But just so in your head, you're now separating two completely different concepts that we talk and we use the word attenuation, but diffuse attenuation, beam attenuation, completely different. Okay? Yeah, so this one is denoted often by KB. Downwelling, diffuse attenuation coefficient, this one by questions? Okay, so now, why do I like it? The beam attenuation, it's a well-defined quantity for a given acceptance angle. I don't have to do any corrections. Other than take the measurement, I don't have to correct for anything. We talked about scattering correction for absorption, here, I use a single measurement, it corrects for itself. There's no attenuation along the path, which you have to correct for some backscattering incidents. So I don't have to do any other correction. It doesn't depend on the polarization state of my source. I don't have to worry about that. And I have a long history for these measurements. So what do you think is a typical distribution of beam attenuation? What do you expect it to do? So now I'm in the ocean, I'm doing measurements. Where should I expect it to be high? Where should I expect it to be low? Okay. Again, I'm trying to build intuition as to what should I expect when I put this in the water. So I have that here. And this is the beam attenuation. And I'm asking you, how do you expect it to go? In the ocean? Yes. High in the red. So, and we're measuring it 60 nanometers. We talked about that, right? But I'm asking you, how is it distributed in the ocean? You've seen that. I'm asking for people who've never seen the profile. What do you think it should look like? Where do we have more material in the surface? Okay, so the surface I expect it to be more. And why do we have more material in the surface in the ocean? Fire. So here where there's light is fueling both particles, I have it high, then it's going to go low. And then what happens when I get close to the bottom? I can have more of resuspension, so it can go higher. And sometimes I might have in the middle suddenly what should that be? Right? No, this is not a failing line. So what you're thinking is if particle settle, if they slowly settling near a density, you can have a big do something like that. What? Deep growth maximum, so that's going to be closer to the surface. You're right. So if I'm here near the surface, so sorry, I might have an area where there's more biotechnology because They need nutrients and sometimes they even want to, we're, I'm sure it's like that. But think of horizontal process. Think about a shell. I have a shell here, and then it falls down. This is the imagery. And then I can get detached naturally with it that I will see in the middle of the water. It's a horizontal process, it's not a one-D dynamic. But you see that, particularly in not in any time of the Oregon coast or the California coast, where you have a shelf that's rapid. So, what do you think we learned from measurement at a single wavelength? So I have a single instrument. This is what I have, and I'm going to do it. What can I do with it? What they tell me about the body? Yeah. Concentration, that's it. I have lots of particles, I have less particles. Nothing about the size division, nothing about the characteristics, because I'm doing a single measurement. So everything I can say is just, there's a lot of it, there's not a lot of it. And we're very lucky in the ocean because things change, concentration change by orders of magnitude. These 3 orders of magnitude, whether it's VOC, whether it's chlorophyll, things change a lot. So even if I don't know the composition, so exactly the index of refraction or the shape, I still can say something about the concentration with a symbol. So we talked about so what are the particle affecting my measurement? So we said here we have biofactor. Here we probably have sediments, and here's some. It's coming off the shelf. It's some organic and some inorganic particle coming, probably bad. It's like 400 meters. And we talked about processes that might make them. So here is a distribution, just like we just got. So this is a combination from this is a transect from a paper by Gardner, and indeed you see what you just said. It's higher in the surface, and then in some places we get in higher depth. And here we even have mid-water maximum. And it helps to have this in mind because if you the first thing you look is it consistent with our view of the ocean. Doesn't mean they're correct, but at least they're consistent. When you look at data. This is the paper that changed my, I just thought about it, it completely changed my paper. An amazing paper. So the paper is about the non-correlation of vertical structure of light scattering and chlorophyll in saltwater. Now, why did they have to say those words? Because in other papers, particularly by a group in France, what they found is that there's a really nice correlation between scattering and chlorophyll in the surface ocean. Very nice. In the surface open ocean, chlorophyll can predict the attenuation and scattering relatively well. But if you try to do it into vertical, it doesn't work at all. Why? Because as somebody mentioned here, there's a chlorophyll lack. So here what we have is we have density. This is density, these lines are density. These are 3 stations in the North Pacific. We have beam attenuation, that's the solid line, barely changes some, but not a lot. And then we have chlorophyll here. This chlorophyll trace, and it's not quenched because I think it's at night. But look at that. Changes significantly here. The scale is, that's a scale of fluorescence, it's a scale of a factor of 3. And we don't see the beam attenuation changes at all. It's barely changing from 0.4 to 0.44, 10%, while fluorescence changing factor of 3. So you cannot use scattering as a measure of chlorophyll. But why did this paper change my career? Is because when you look at chlorophyll and you divide it by, here they do the particle volume, but you get the same information. It behaves in a very predictable way. It goes down, it increases just like light decreases. So there's more chlorophyll beam attenuation at depth in a pattern that mimic how light is lost. What does it tell you? tells me two things. One is the reason relationship between this total particle volume and also beam attenuation and the particle that has growth within them. So I can use what I took from it is just the opposite of what most people would take from this sample. Is that we can use beam attenuation, we can use back scattering to get information on the mass, the biomass, the carbon mass of fiber. And the reason this is happening is because the light decrease, they have more chlorophyll inside of the cell. Responding to light. It's like your house light. You take it from outside, you put it inside, and suddenly it becomes greener, more chloroplast in every leaf. This is exactly why you're getting this pattern. This is a pattern of photoaccumulation. Things growing at that have not a lot of light. In fact, have chlorophyll. But this would not look like this if the beam attenuation had nothing to do with fire. If beam attenuation was in a kind of fire plant, you wouldn't get this. And after I recognized this, my friend came to town. He was working somewhere else, and I told him we need to go for coffee because Mike was working only on this, and everybody wants carbon mass, but this is pigment mass. And since then, we had a very productive relationship about using scattering and using attenuation to give information outside. It's not yet accepted by the full community, but it has been fun for us to be an extremely useful avenue for research.
That discussion was missed in that paper, they didn't talk about photoaccumulation.
They might have talked about it here, but if you read this, the take-home message is there's no relationship, right? And this tells me the reason relationship because you have to bring light into it at the same time. Yes, Colin.
They did talk about it, and it's, I think, really nice comparing this paper with the 1980 paper by John Sullivan, which talks about the surface chlorophyll maximum and the different processes that can lead to subsurface chlorophyll maximum. One of them can be mentioned in the surface and measured fluorescence at during the day, but the other one is that it's not a biomass maximum, but that it's actually photoaccumulation to have more chlorophyll at depth. And so they mentioned that in this paper, and what I think is also really amazing about it. To me, it was one of the first papers in my career where it was looking at biology, how physicists look at biology. It came up with the same answer as biologists looking at biology. And it was just a really amazing time to start in biooptics because of that scene that we were doing size.
So, like all IOPs, beam attenuation depend on size and composition. And as we went through Wayne's talk, there's many ways to look at it. So there's these parameters that we get out of neat theory, but now I try to deconstruct them for you. If this CX is attenuation of a single particle, and you look at how it changes with particle size, for properties, this is a phytoplankton or an organic life particle. And this is a wavelength close to the one of the transdusometer. The bigger the particle, the more beam attenuation you're going to get. Bigger particle, more beam attenuation. Just take one particle and I grow. That's clear? Now I'm looking at that same property, but now I'm normalizing by the geometric cross-section. So now I'm taking exactly that, the beam attenuation of a single particle by dividing it by its cross-section area. What do I find? Initially, it's very low. And then as the size of the particle grows, it grows up, oscillate a little bit, and then stabilizing on the value of G. So twice the cross-sectional area. For large particle, this is 1 micron, by the way, this is in micron, yeah. So this is 1 micron, and this is 10 micron, and so phytoplankton are in this region. So Generally speaking, we're finding that we extract twice the cross-section area. But now if I do it per volume, I'm taking the same attenuation divided by the volume of each particle. So attenuation per particle divided by this volume. Volume is important because that's mass. Now I'm getting a peak. Around about 5 micron, I get the most bang for the buck. The most attenuation per carbon, I'm going to get around 5 microns. That helps us explain why we use optics to do phytoplankton and why we use acoustics to do zooplankton. Yes.
It's about your phytoplankton on the rock.
These.
So which phytoplankton and when you include them to the attenuation? The lowest the mass basis.
So it's not equal. Your contribution to beam attenuation is not equal as function of your biomass, or at least volume mass. Might be that, again, if you have a large vacuum, you don't have as much biomass in terms of carbon. Right? And this is a classic resonance curve in physics. There are sizes that interact the most with waves. Your drum has a certain sound that it gives you the most because it has to do with its size. Your violin versus your viola versus your double bass gives you a different sound because of the size. This is in the opposite. This is what resonates with it. So different sizes will give you different responses. Okay, remember that. And this is for solid particles that are sphere, but that sphericity is not a big factor in here. Now I can look at this divided by volume basis. So particle beam attenuation divided by the volume. And now I'm looking at the same wavelength that I looked before, but I'm looking for particle of different composition. So this is 1.2, 1.15 to be like a sediment. And here I'm at the phytoplankton range. And what we see is that the size that resonate changes depending on the index of refraction. I tend to have this resonance for smaller particle, for a more refractive particle, a more sediment-like particle, and less so as I go towards the phytoplankton. The other thing, which is kind of interesting, if I do it and I also add absorption, remember absorption is this N prime business. If I add absorption, that's going to change my beam attenuation to volume at the low end because I have almost no contribution of by scattering there. But in the rest, it's not a big change at all. Because most of the contribution is scattering and not absorption into my total attenuation. So for very small particle, absorption is very important for attenuation, but not for large particles. It's not contributing significantly. So this is for one single index of refraction. Now, remember what I told you in the math that we did? The index of refraction of phytoplankton is low, not because they're made of low index of refraction material, but mostly because it's diluted by water. So if I squish a phytoplankton, it's going to be like this. You're going to see it in water. But if it's swelled because it's full of water, its effective index of refraction is very low. And I forgot to give it to you this morning. So, interestingly, so this is the interesting thing. I just told you how beam attenuation is so affected by volume. And then I'm telling you empirical beam attenuation to mass ratio only changes by a factor of 2 between organic and inorganic particles. But that's, yeah. So how come this happens? How come between organic and inorganic particles, there's no big change between beam attenuation divided by mass? Even though the index of refraction changes, if you look here, look at those changes. This is a big change. A phytoplankton is here 0.4. A sediment might be here 1.6. I have a factor of 4 difference in the amount of scattering attenuation I would expect per volume or per mass. Yet the maximum I find is maybe a factor of 2, about a factor.
Yeah, we change it, volume, mass, and density.
Exactly. So it's because I do it for dry mass. You're absolutely right. If you take a phytoplankton, like then I dry it, I'm back into my relatively high density fraction. So I'm not as different as I might be if I did it by wet mass or by volume when it's in the water. So yeah. And this is an excellent paper, and I'll probably will expand on it next week about how to build the optical properties of phytoplankton from what they're made of. So single wavelength beam attenuation, these kinds were found to correlate well with total suspended mass, particulate organic carbon, particulate volume, phytoplankton pigments in area where light in the mixed air is stable and light is relatively constant, and even with phytoplankton biomass. I didn't show that. We have a paper from 2006 on that. So here are 2 examples. This is Peterson, who worked with von Zanneveld. This is relative to total particle volume. Here's beam attenuation. And here is a paper by Bishop looking at POC versus beam attenuation. And this is particulate organic carbon and particulate dry weight, 2 different things that they looked at. But both correlated well with beam attenuation. And this is middle of the ocean. This is, I think, coastal environment. So Paul Hill did a review of this ratio, beam attenuation divided by mass in coastal environments. So many of you who work in estuaries and things like this, and if you take all this paper, find that most of the data sits in a relatively tight environment, CP to SPM. So beam attenuation to particulate mass. All those are at 660 nanometers. And then when SPM becomes really large, it starts falling below. And then we have these outliers from Bishop, we're not going to talk about. So mostly it's within a factor of 2 from the lowest to the largest most values, and then we have some. Why do you think that might happen? Why might we have a maximum SPM? I mean, as SPM becomes really large, this might hang down. Yeah,
Multiple scattering.
Multiple scattering might be. So multiple scattering, what would it do to your measurement? Beam attenuation, how would beam attenuation be affected if you have multiple scattering?
I mean,
would give you maybe if it comes back to your beam, less beam attenuation. So that could be one reason. What do you think? How do you think particle size distribution change as you have more and more and more particles? They tend to be larger particles. The more attenuation you have, typically the suspension events, and a strongly suspension event means it's larger particle. So concentration, we're normalizing that. So this is beam attenuation divided by concentration. So if you have more big particles, what happens in terms of beam attenuation? Or let's talk volume scattering. It'll be more forward beam. I will collect more of the scattered light. I'm not going to be as efficient for mass. So that was our explanation was that it's probably due to the finite acceptance error. Is that you're not as effective in getting the attenuation because you're collecting a lot of the forward scattered light. So we talked about that. Okay. So in the ocean, there's not just solid particles. There's a lot of aggregates. Particles that are this combination of many. And it's very interesting how our aggregate behaves. Now, you notice that on one hand, I tell you that beam attenuation is extremely sensitive to a specific size particle. Beam attenuation per mass. You can think about this as beam attenuation per mass. So it's very, and then I tell you, yet beam attenuation per mass is not changing much. Here, I'm telling you, it's not changing much in the ocean. And we know size distribution changes a lot. So yes, maybe that affects this, but overall, things are extremely stable. So, and the reason I'm repeating that is because we think aggregates can play a role, and I'll explain to you how. So this is an example from the field. It was in Wayne's thesis where we deployed two lists side by side, and in one of them, we churned the particles. This is the beam attenuation we measured. You see, it's not very different. This is the change in size input. It's quite different. And this is the change in phase function. So we basically, by passing them through a pump, took aggregates and blasted them. It's a big change in size, but it's not as big a change in beam attenuation. And what's happening is these loose particles are mostly acting as cross-sectional area. And so if I look at it from that perspective, and I go back to what I showed you before, if beam attenuation is proportional to cross-sectional area, like here, if beam attenuation is proportional to cross-sectional area, and I preserve the cross-sectional area when I form aggregate, I'd expect this to be relatively high. My beam attenuation to be gravity constant also is a function of mass, because mass and cross-sectional area for aggregates with a fractal dimension with 2 on a 3 number that is going in the same direction. Mass becomes a fractal property, and you can dive more into it in those papers. But yeah, we're going to stop there. Also, there's Dale cycles in beam attenuation. Dave Siegel, Marlon Lewis, Clancy Close, all have observed very nice Dale cycle in beam attenuation, which they're using now to calculate things like net community production. You assume that at night it's lost to grazing, and during the day it's both grazing and growth. You can decouple the growth from the grazing and get information actually about primary productivity. They use it also for primary production. The change over time is your net community production. The Dale cycle is actually used to do primary productivity. Again, it's under the assumption that at night all you see is loss, and the day all you see is both, and that loss during the day equals loss during the night. Another thing that is used, beam attenuation is used for, and it started with pioneering work by Bishop, but Meg has pushed it way along, is to use a beam transmissometer as a segment collector. So I put it like this. Hopefully they're far enough that the material can settle on the window. And if I start measuring beam attenuation at part of that, at a certain depth, start falling down, then that tells me something about carbon extra. Something is interesting because of the carbon extra. Something we really want to know. Because that's what the ocean thinks in the atmosphere. So you park it at different depth, and you're measuring how export is different than different depth. Meg is the specialist to go to if you want to learn more about it, but this is the type of instrument they put on floats to do that. Now we talked so far about the scalar beam attenuation. Now I'm going to talk about the spectral beam attenuation. So again, now with one wavelength. One wavelength is changing daily, one wavelength is changing with depth, one wavelength. Now, it turns out if you do the same calculation we talked about before, beam attenuation divided by volume, the peak also changes with wavelength, the peak response of this particle beam attenuation divided by the volume. I get a response to larger particle at 660 than I get at 420. So the same index of reflection. that tells me that basically my instrument is a window to different sizes of particles at different wavelengths. So by looking at the spectral change in innovation, I should have some information about size of these micron size particles. So it's like the instrumental filter. The instruments are ways by which we see the environment. Think about them as glasses we have on. And indeed, there's a theory from a genius sphere, non-absorbing ones that tie this particle size distribution, the one that we just heard about from Wayne, the power law size distribution, where these, if you have this kind of particle, and he was doing atmospheric work, you predict that you have this type of beam attenuation. It will also be a power law as function of wavelength, and these two are related. This is from non-absorbing, perfectly spherical particle, going from 0 to infinity. Now in the ocean, we don't go from 0 to infinity. We don't have perfect sphere, but this links what we'd expect to have. So the steeper the size distribution, we'd expect the steeper the spectrum of the beam attenuation. Okay. I know it's a lot to digest in one talk. And we went and measured it in the ocean. This is an AC9 meter that was deployed on the boat and went up and down. This is that parameter, the exponent that we fit to the power law. And this is the particular beam attenuation, which is like mass. And we typically expect that the more mass there is in the water, the bigger the particle. So this is why I'm using that. But they also took, I was not on that cruise. This is from a big DRI of the Navy called Coastal Mixing and Optics. I came as a postdoc. But they also had, Gardner measured size distribution. So we had the steepness of the size distribution. You can see both are behaving quite similar. And when there was a hurricane that broke big particles into smaller ones, you see them both in the beam attenuation and as well as this. Now, the difference is not exactly 3 as theory would tell, but it's not that far from 3 in terms of values. This is from 1.2 to 4, so 2.8 difference. This is 2.4 to 0.3, so 2.1. But overall, we see the same trend. And this suggests to us, therefore, that we can use the AC meter to tell us information about size. This is from the Tara, what you just saw, and we just saw exactly the same thing, and the distribution. And notice that the scattering spectrum is less steep than that of attenuation because of the effect of absorption, as you heard from Wayne. But now I want you to focus on this feature. You see this little feature in beam attenuation? Anybody knows what causes this feature? It's not chlorophyll re-emission, it's chlorophyll absorption causes this. It's called anomalous dispersion. There's a theory for it in Van der Hal's book. You can find more detail. So in the past, so we had a student in the class, and we suggested it as a problem. Emmanuel from Santa Cruz was a student in the class. And we told the class this could be an interesting project to see how good this is in predicting chlorophyll. And he did this, and he wrote a very nice paper. So he's looking at the difference between what you have if you don't have a strong absorption peak, and what you're measuring versus what you'd measure if you did not have. So he's fitting the power law. So he's looking at this residual, and he found that from this residual, you can find information that is very well correlated with chlorophyll. So now with the AC, the C side of the beam accelerator in the information of chlorophyll, and there's a size index of phytoplankton. So I'm not going to get into in this. And another student, Niels, in his thesis, actually measured size distribution of phytoplankton and found this house steeper size parameter to be the best predictor for phytoplankton size distribution, not particles, phytoplankton. There's also seasonality in these properties. This is data that Colin collected in the Gulf of Maine. Colin used to run a much bigger operation with many buoys. Now she has the buoy here, where she could have AC meters out on buoys. And she was able to use changes so this is from August to January, this is the changes in temperature at different depth. And these are changes in the absorption and as well as in properties of beam attenuation and backscattering ratio, dB over B, along the season. And you can see those changes that were directly related to changes in the kind of phytoplankton we had in the water. But this jump in gamma and the change in gamma as function of time was indicative of changes to smaller species as we go down the season. And she could separate high and low light adapted. So to summarize, if I had a single optical measurement, it would be this. Beam attenuation is a robust RP, you don't need to correct it. It has a long history as a proxy for mass, and different kinds of mass depending on what you're studying in the environment. The spectral has significant more information, but remember, it's a function of acceptance angle, you need darks, you can worry about your lamps, etc. Thank you. Questions? Yes. Well, you need something that's stable because you want to, you're measuring in the other, let's say here, here, here. And so you want something that, if you do each one relative to the depth where you measure, might change as function of your food. The user instrument is stable, you need more side affected by pressure, and then you can only, there's a point if you use equal masses where you say this is by zero. I don't know how much mass is there. That's okay. But it's often extremely hard, but it's still also my instrument is not being used in the a very good instrument, well characterized, I know it's not affected by pressure, and I can therefore use some measurement along with these as my equivalent. And it's very good water. And everything is relative to that, which is okay to do. But it's under all this factor, and you say it in the table, you have to switch. Green, it's got code. I mean, people have found that they get negative beam transition because they're bubble in the water. The time rate, there's a whole variety of ways by which you can water that's not as clear as the clearest water the time rate. So how do we want to do it with their presentation? We have lunch coming in 20 minutes. What? We have plans to do one.